In this video we're going to derive a differential equation which describes the motion of a wave in one dimension. So what we have in front of us here is a graphical calculator called Desmos. You can get it online, okay, and I've put a link down below where you can go and get it, and also a link to this particular simulation that you see in front of you, so you can just download it, you can play with it yourself. Okay, so what we have here is just a cosine wave. Okay, so there's a cosine wave there. Now along the y direction is the height of the wave, and along the x direction is just the distance along the wave. So you can kind of think about this as a water wave just splashing against the beach, okay, when you're down at the beach. Now y is just the height of the wave and x is just the distance along the wave, and what we've done is we'll take a snapshot in time. Okay, so the snapshot in time shows this cosine function. So we know that we're trying to generate a differential equation, so we know the differential equation is going to have y, the height y, is going to be some function of the distance along the wave x. Okay, now it's not only going to be a function of x, it's only going to be a function of time as well, because if we allow time to continue, so that's the wave now coming along and hitting the shore. I've actually got it here just going backwards and forwards, okay, but you think of the wave come along hitting the shore, then we can see that if we were to pick one particular point along the x direction, say x equals 2 here, the black one moving up and down, then we can see that if we think about this point here at the end of the line here, there's just a little boy sitting on the wave, just bouncing up and down. Then we can see as time changes, then the y position varies with time. Okay, so that means that our equation that we're going to derive is going to be some function of the position along the x direction, and we take a snapshot. So it's going to be y is going to be some function of the position along the x direction, but y is also going to be some function of time. Okay, so we're going to now have to go and look at deriving an equation that's going to have some spatial variation, and it will have a time variation as well. Okay, so let's go ahead, we'll stop that, and we'll go ahead and we'll go and see if we can derive something that's going to approximate this. Okay, so the way we're going to do this is, if we don't need to think about it in terms of a wave, we can think about it in terms of a string, so we don't lose anything by doing that. So if we imagine we have a piece of string, so now this is a small segment, an infinitesimal segment of string, okay, and we give that point the point x, and the other point on the string, we'll call that x plus h. So the distance of the small segment of string is going to be h. Okay, now there would be another piece of string at the other side, on the right hand side here, that would be tending to drag the string in a particular direction, and also a piece of string on this side here that would be dragging the string in a particular direction. So what we're going to have is, we're going to have tension on each of the ends of the string. So the tension is going to be tangential here to that point, so we could just try and draw that out. So there's one force of tension here, and there's also a tension force here in this direction here as well. Now all the way along this we're going to make some assumptions. Okay, so the first assumption that we're going to make is that each element of the string can only move up and down. Okay, and if we draw our axis system, we call that y, and we'll call that x. So each piece of string can only move up and down. So we've seen that on the previous video, on the video there, whenever we looked at each element moving up and down. Okay, so what we're really saying then is that if we would take these tensions, we can resolve them into a horizontal and a vertical, and this one here can be resolved into a horizontal and a vertical tension. Then it means that assumption number 1 is telling us that if we added up all of the tensions in a horizontal direction, those would all equal 0, okay, because the string's not been pulled in either direction, okay, so the overall forces in the horizontal direction must be 0, okay, so that's our first assumption. Now we're going to work out our wave equation using Newton's second law. So Newton's second law says that force on that little element of string is going to be the mass times the acceleration. Now the mass, we're going to write that down as a mass per unit length. So if we take mass per unit length and we were to multiply it by the actual length h, then we would have the mass of that particular length of string. But we're going to make it a little bit more general. Well, let's assume that maybe the string can be a little bit thicker at one point and a little bit thinner at another point. It means that the mass per unit length will also be a function of the actual length along the string, okay? But we'll take that out at the end. It's just to keep everything as general as we possibly can. So that there is going to give us the mass. Now the acceleration, it's just the acceleration of a single point. So we fix the value of x, okay? So the value of x gets fixed and we just allow that point to run up and down, okay? Just as you've seen in the simulation. Now it means that the acceleration is the second differential of position with respect to time, so it's going to be partial squared y by partial t squared. Now it's partial because we've fixed x, okay, so it's a function of two variables and we've fixed one of the variables, so we've got to use the partial differentiation. So this is the mass times acceleration. Now the force, the only forces that we're going to have are the vertical force here and also a vertical force there. So if we're going to write these out, so we call that angle theta and we call that angle there theta, then this height here is just going to be it's going to be a t sine theta, and that height there would be a t sine theta as well, but it would be in the opposite direction, so it would actually be minus, okay, so that's a positive direction and that's going to be in the minus direction, okay. So what we could do is we'll write that out. So we're going to add these two vertical forces, tensions. So we would have a, let's write it down here, we would have a tension. Now the tension on the right hand side is at a point x plus h at time t, okay, so we're just saying that that's the tension there, okay, but it's the tension at that particular point x plus h, and we've taken a snapshot at time t, okay, so that's all that's telling us. Now it's going to be that, and it's going to be the sine of the angle theta, but it's the angle theta again at a point x plus h at time t, and will be minus the tension at the other side here, which is tension at a point x at time t times the sine of theta at a point x at time t. So that whole thing there is going to equal our mass times acceleration, which is going to be our rho x h partial squared y by partial t squared. Now what we can do is we can take the h down, so rather than writing the whole thing out, I'll just again and just rub that h out. So take the h out and we'll just take it down here, okay. So we'll take the h down there. Now what we can do is we can take the limit as h tends to 0, okay, so I don't know if I can squeeze it in there. Limit as h tends to 0. So that whole thing there is just a differential, okay, so all that's going to give us is our partial by partial x of t of x at time t times the sine of theta of x at time t, and that whole thing there is just going to equal our mass per unit length times the partial squared y by partial t squared. Okay, now we're going to go on and we'll look at our second assumption, so that's our first assumption up here. Okay, and our second assumption here we're going to make is that the vibrations in the string are very small. So what you're really saying is the y displacement, so I'll just put y, so the y displacement is small. Okay, so we're really saying that the string waves up and down, but the actual height of the wave is actually small, okay, relative to the period here, or the distance. Okay, so that's our second assumption. Now if we make that assumption, it means that we can get rid of this sine theta and we can change it into something that's a bit more useful to us. So the way that we do that is that if we were to again look at a small segment of that piece of string, I'll try and draw this out reasonably. So if we took a point here and we took the gradient at that point there, so I'll just come along and we go bump, bump, bump. Right, so we've got the gradient at that point there, then really we can say the gradient of the point is going to be equal to sine theta upon cos of theta. We know that because whenever you, if you were to draw out the a little circle there with your Pythagoras, then you could say sine theta is just going to be y upon r, and cos theta would be x upon r. So sine theta and cos theta would just really be the value of our tan theta, which would be y upon x. Okay. Okay. So it would mean then that if we were to draw this line here and we could continue this line along there, then what we'd be looking at, the gradient would just be this distance here upon this distance here. Now if we were to ensure that the variation y is very, very small, okay, it would mean that this length here, okay, the length here, if the height is small, that length there is approximately equal to that length there. Okay, so that length there is approximately equal to that length there, but we know that cos theta is if we say x upon r, so that's our value of x there, and the length of this little arc here is r. Okay, so that's the length of that little arc there is r, and that length there is x. Then we're saying that these two distances x and r will be approximately the same. So if we say that, then it means that x is approximately equal to r, so it means that cos theta is approximately equal to 1. Okay, so that would mean that all we would be left with this would be our sine theta, and we'd be able to say that our sine of theta, well, sine of theta would be y upon x, but it would be the differential. Okay, so it's going to be the differential partial y upon partial x, and it's the partial differential because we're fixing the value over time. Okay, so it means that we can go back in here, and for this sine theta x at t, we can just replace that with partial y by partial x. So we're going to end up with then partial by partial x of our tension at a point x at time t times partial y by partial x, and that's going to equal our mass per unit length, which is a function of the distance as well, times partial squared y by partial t squared. Okay, so that there then is really the equation that we're looking for. Okay, so that's a kind of write it out in a reasonably general way. Okay, but we're going to make another couple of assumptions just to simplify this and get it down into something that looks very familiar. So assumption number 3 that we're going to make is that this value here, the tension at x at time t, we're going to say that that is equal to some constant. Okay, so we'll actually just give the constant a name, we'll just call it simply t. Okay, so what we're really saying is that the system is the string is perfectly elastic. Okay, so it's really saying as you stretch the string, the tension force doesn't change. Okay, so that's an assumption that we're going to make. So we can make that simply T. Now there's going to be another assumption. The assumption 4 is that the rho of x, okay, so the mass per unit length isn't actually a function of the length, it's just a simple mass per unit length. So really what we're saying is that the string is of uniform thickness, okay, and the mass per unit length is distributed evenly along the length of the string. Okay, so if we make that assumption, then we can say that rho of x is just equal to rho. So it means that then what we can do is we can simplify that out, and we can, because T is the tension is no longer a function of the value x, we can take that outside this differential here. Okay, so it means that you could just have a T, okay, and this is going to be simply the second differential, so you're going to have partial squared y by partial x squared is going to equal rho times partial squared y by partial t squared. Okay, so if we can then rewrite that, we can take the p down, and I'll just flip it around the other way. So we're going to have partial squared y by partial t squared is going to equal t upon rho times a partial squared y by partial x squared. Okay, and that there is the wave equation. Okay, now you'll generally see that written out in a general form. Sometimes you'll see it written as UTT, so that's just the second differential there with respect to time, is equal to c squared times uxx, which is the second differential of position, and that c will be equal to a root t upon p. Okay, but that's the derivation there, and as you see that the same thing happens here. You see this cropping up all the time in physical systems, where you have a constant here which is a measure of t, which is a measure of the springiness, it's a measure of springiness of the system, and the rho, which is going to be a measure of the inertia. Okay, so you always get this measure of this ratio of springiness to inertia. Okay, so that's all there is to this. I'll go over the next video and we'll look at solutions for this equation, and we'll derive the famous D'Alembert's solution. Okay, so thank you for listening and goodbye.